Hello children, welcome back to the channel. Today we will be taking up or starting the important chapter of work, energy and power. Now, up till now what we have discussed is that force and the effect of force in the motion of object, right? With the Newton's laws of motion, how a force applied to an object either changes the velocity, either increases or decreases the velocity, and so on, and how acceleration is produced, and what distances will be traveled by the body after application of a force, and all these things. Now, what it does is that whenever there is a force applied to a body and it affects its motion, what it does is that it actually displaces the object from one point to another. Displacement is an aspect of object, because we always measure what is the displacement of the object, or we identify motion by change in position of the object. So displacement is inherent to the motion, and so the laws of motion basically talks about force, its effect, the displacement, and so on. So this effect of this force, that is the force displaces an object, is measured in terms of work. In other words, what we are saying is that if there is a force applied to a body and there is some displacement in the body, produced in the body, let's say we have an object here and the force is applied here, F, and the object moves from here to displaces through this much, then we say that some work has been done. In other words, that if there is force acting on a body and there is a component of displacement of the body in the direction of the force, then we say work has been done. Okay. So if you have to define work, we say that work is said to be done if the force is applied to a body or an object, and the object has component of displacement in the direction of the force. What do you mean? Why I am saying that component of displacement in the direction of the force is that it is not necessary that we always have the force applying in the same direction as the displacement. Let's say a generalized case. Let's consider a generalized case like that of an object standing on a plane. Let's say this is the body, and the force is applied in this direction, say F. And as a result, there is a displacement in the body along the horizontal or along the plane. Let's say this is the displacement. So clearly force and displacement are not in the same direction. There is an angle between the force and the displacement, and that angle is this one, right? Let's call this theta. So what is the component of displacement in the direction of the force? We can easily find it by resolving this vector force or the displacement vector into two components, one along the force vector and one perpendicular to the force vector. Okay, so this component of the force vector, or sorry, the displacement vector in the direction of this is the component of displacement in the direction of the applied force. What is the value? We easily can find it as S cos theta, this direction. So the work done will be measured by the product. Work done will be measured by the product of the applied force, magnitude of the applied force, and the component of displacement in the direction of the force. That is to say, S cos theta. However, from our knowledge of vector, we know that F into S cos theta can be given as F the S. So work done is equal to the dot product of force and displacement, provided this force is constant over the entire displacement. So from this point to this point, when the object is moving, the force's magnitude or the direction is not changing. So for constant force, this holds. What about the variable force? We will go into this in a while. But by definition, work is the dot product of force and displacement. Okay, so the value of this work will depend on the angle between the displacement vector and the force vector, right? So if we say that for theta less than 90 degree, that is to say we have an acute angle between force and displacement, then cos theta will be positive. First quadrant cos theta is positive, right? So the work done will be equal to F as cos theta, which will be positive. So we can simply say that work done is positive. This is the case when the applied force accelerates the body, okay, or when the applied force changes, displaces the body. Next is if theta greater than 90 degree, that is theta is obtuse angle, that means cos theta in the second quadrant will be negative. Under that condition, W is negative. So negative work is done. So work can be positive or negative, right? When we say negative work or when we say theta is greater than 0 or 90 degree. See, one example we already have seen. When we were discussing friction, the object was moving in this direction, say, and the frictional force was always opposing the object's motion. So the angle between the displacement vector and the frictional force was 180 degree or pi, which is -1. So work done was minus of the magnitude of the work, right? So work done was negative. So work done by friction is always negative. We already have discussed this in the previous video. If you haven't seen those videos, then the link to my videos on Newton's laws of motion is given in the description below. You can refer to that. Okay. Now we have seen obtuse and acute and obtuse angle. What if theta equals to 0? Oh, sorry, not 0. Theta equals to 90 degree. Means cos theta will be 0. That is W is 0. So work done will be 0 if the displacement is happening in a direction perpendicular to the applied force. We have already seen an example of this. Can you find that? Remember that? Okay. When we were talking about circular motion, uniform circular motion, we said that the velocity vector and hence the displacement will be tangential, whereas the acceleration or the centripetal force is along the radius. The angle between these two was 90 degree, which means the centripetal force didn't do any work. That is why the magnitude of the velocity didn't change, only the direction was changing. Okay, clear till now? Okay, now we have already seen that work done W is equal to Fs cos theta, right? So what will be the dimension of work? It will be simply dimension of force multiplied by dimension of displacement. Dimension of cos theta, which is a ratio, so cos theta doesn't have a, or any of the trigonometric ratios doesn't have any dimensions. So this will be, force is ml, T inverse 2, displacement is L, so work will have the dimension of m1 L square T inverse 2. And for units, in SI, the force is given by Newton and displacement is given by meter. So unit of work will be Newton meter, which is known as joule or J. And in CGS, it is dyne centimeter which is known as erg. Okay, now what is 1 joule? 1 joule is the work done when a force of 1 Newton displaces a body through 1 meter. Then the work done is said to be 1 joule. So unit of work is joule. Now if it is so, then 1 joule must be equal to 1 Newton. 1 Newton is 10 to the power 5 times multiplied by 1 meter, that is 10 square centimeter, or we can say that 10 to the power 7 dyne centimeter, that is erg. So 1 joule equal to 10 to the power 7 erg. Okay, now in terms of the rectangular components in 3 dimensions, force can be given by Fx I cap, Fy j cap and Fz k cap, and the displacement is similarly given by Sx I cap plus Sy j cap plus Sz k cap. So work done equal to F dot S. From our knowledge of dot product, we can say that W can be given by Fx Sx plus Fy Sy plus Fj Sj in terms of the components, rectangular components, 3 dimensions. Okay, now let's consider the case of variable force. That is to say, the body displaces through this much, say S. However, the applied force F now is not constant over the displacement. Under such condition, how do we find the work done? To do this, what we do is that we make use of the calculus. Okay. So what we do is that we take a very infinitesimally small amount of displacement here, say, let's call this ds, and we assume that the force is practically constant over this infinitesimally small interval or small elementary displacement. So the elementary work done for this small displacement will be F dot ds, where F is constant over this part. So to find the entire work done, W, what we need to do is that we need to integrate this equation from its initial position, let's call this say S1, to the final position S2. So this is S1 to S2, the position vectors, right? So S2 minus S1 will give us the displacement vector. Okay. So from initial position to final position, and then what we do? We take the integration of F dot ds. However, if we say theta is the angle between F and ds during that at that particular element, right? Then we can also say that S1 to S2 F ds cos theta. So if we integrate this equation, we will be able to find the total work done. Let's take an example to make this clear to you. So we are given that a force 7 given by F equal to 7 minus 2x plus 3x squared is applied to an object at x equals to 0, and it displaces it to x equal to 5 centimeter. Sorry, not centimeter, 5 meter. And 5 meter. And this force is in Newton. You are supposed to find the work done. So what we will do? We will notice here. First thing we will notice is that the force is given in terms of some constant, then the x components only. So it doesn't have y or z components. So force is along the x-axis. So this F dot ds will simply be F into dx. Only the x component is there. So W will be integration from the initial position, that is 0 to 5 meter, into F dx. If we substitute the value, we will get integration 0 to 5, 7 minus 2x plus 3x squared dx. After integration we get 7x minus 2x square by 2 plus 3x cube by 3, and in the limit 0 to 5. Fine. So each term has 0 x in it. So we substitute f 5 first. 7 into 5 35, minus these 2's will cancel, x square is 25, 3's will cancel, plus 1 25, minus 0, because if we substitute 0 all the terms will be 0. So if we simplify this, what are we left with? 125 plus 10, 135, right? 135 joule. This will be our solution. So in case of variable forces, we can always use this equation as we have seen in this example to find the total work done. Now a question naturally arises that how does an object or how does a body or an agency does work? It must have certain amount of ability in it to perform this work. Otherwise the work will not be done. So this ability of an object or an agency to do work is known as the energy of the work of the body or the agency. So energy is actually how much work a body can do. For example, if you have this pen here and release it, how much work this particular body can do is stored as the energy of the body. Okay. Now the energy has a wide range of forms. Starting from the mechanical energy, like the object when they are moving or because of their position or because of their configuration. You have spoken about thermal energy. When you burn an object, energy is released. You have spoken about nuclear energy, you know about solar energy, wind energy. All these things are different forms of energy. However, what it measures is that how much work the wind can do or how much work the object can do. Since it measures the capability of doing work, so energy is equivalent to the amount of work the object can do. So in numerical terms, energy is equal to work that can be done by the object. So to measure energy, we always measure how much work the object can do. Now, as far as we are concerned, because we are talking about motion basically, so we will be interested much in the mechanical form of the energy. Sorry. Mechanical energy. Now, mechanical energy can mainly be divided into two forms. One is the kinetic one, the other one is the potential one. These are the two energies that we will discuss in this chapter. We will reserve potential for the time being. We will talk about kinetic energy. Now, what is kinetic energy? Kinetic energy, by definition, will be energy contained in the body by virtue of its motion. For example, you have a ball moving in a direction and it hits an object, say an obstacle, and the obstacle moves a little further. For example, if you talk about the billiard game, then the cue ball goes and hits the ball and the ball moves. So the moving object, the cue ball that was moving, contains certain amount of energy by virtue of its motion, which it imparts on the other ball so that it moves further or in certain direction, the desired direction. So energy contained in a body by virtue of its motion, by virtue of motion, is known as the kinetic energy. Okay, so how do we measure it? We already said that energy is measured in terms of, or energy is equivalent to the ability to do work. So how much work the object can do will give us the energy. So let us say when the object is moving, or let's say let's take the equation of work. Okay, and let's say in this case that the angle between F and ds is 0 for simplicity, which will give us this equals to F ds directly. Okay, so since ds it is dw. However, F is given by m into acceleration, that is dv by dt. This is force. Force is mass into acceleration of the body. This is mass, this is F, and this is the displacement state. So the force F will be m dv by dt. Okay, into displacement, right? Or we can rewrite this as m ds by dt into dv. Therefore, we can say the work done is equal to m ds by dt is v into dv. So total work done from the initial to the final position. So let's say the object was initially at rest. After the application of the force, after it has traveled through this distance, say u equals to 0 and the final velocity v becomes equal to v. So the object was at rest, the force was applied, it displaces through this distance of say it's displaced by s, and after this displacement the velocity acquired by the object becomes v due to the applied force. So the net work done w will be given by integration from 0 to the final velocity m v dv. M is a constant, will not change, so it will come out m v will be integrated, will be v square by 2 0 to v. That is to say w will be equal to half m v square. However, we have already said that this will give us the value of the energy contained in the body, so this will be equal to say k. Let's say kinetic energy is given by k. Now from here what we can also see is that we can rewrite this as k equals to half m square v square by m, just multiplying the numerator and denominator by m, which is ultimately multiplied by 1 only. So this is equal to 2m in the numerator. M square v square is what? mv whole square, which is p square, where p is the momentum of the object at the end of the displacement. So it will be p square by 2m. That is to say kinetic energy equal to p square by 2m. Or we can simply say that the momentum of the object at the end of the displacement can be given by 2m into kinetic energy. Okay, this is a very important relation. We will encounter this many times in this year as well as in the next year in class 12 when we talk about modern physics also. Okay.